Okay, well, welcome back, everyone. First, I'd like to thank the organizing team for putting together this whole program and this week in particular. And so indeed today, I'm going to give a lecture on the Blackboard, whose goal is really to give you the basics of quantum computing. So for those of you who are already experts, probably you won't learn much today. So today is basically standard things to know on quantum computers when they're perfect. And what I mean by perfect is also when you have quantum error correction. So now you know that quantum error correction is feasible, so you can imagine that today is the perfect world where you have quantum error correction. So that's what I will call a noiseless or a perfect quantum computer. And tomorrow we will go into in the real world and talk about what we can do when we have decoherence. So you'll see it's much easier because we have much less choice, but that's nevertheless interesting. And so to start with, I'm going to really lay the groundwork. And so there are things that Mazia already talked about that I will cover also, but in a more maybe slow way. So please feel free to interrupt me at any time. That's the goal. And so first I'm going to start with a qubit. And so essentially I'm going to introduce a bit what gate-based quantum computation is today. And so first we need to talk about how we describe a qubit. And so as probably all of you know, a single qubit can be described by a wave function. And traditionally we call it here with the notation of a ket. And this ket we like to write it as the superposition of two basis states, 0 and 1. And the definition of the 0 and 1 is usually taken to be the eigenstates of an operator that is called sigma z, such that sigma z applied on 0 is 0 and sigma z applied on 1 is -1. So, and you will also see that sigma z, if I write it in the basis of 0 and 1, is, of course, this matrix. And I will also use a lot in the lecture other famous of these matrices called the Pauli matrices. So sigma x is one of them. It's defined as the matrix that flips the spin. Why? Because, so if you remember that first column is 0 and second column is 1, and then 0 turns into 1, and 1 turns into 0. So that's also what some people call the bit flip matrix. And last, I will also use extensively the sigma y matrix, which is defined in this way, here with -i, the complex number, I, 0, still in the basis 0 and 1. So these will be the basic algebraic blocks I will use. And here, we need to add a constraint on these coefficients. So alpha and beta are complex numbers, such that their modulus squares to 1. Why? Because we want to ensure that the wave function is always normalized. Okay? And the fact that I have this constraint here also means that I can always find a complex number. I can find an angle, theta, such that alpha is cosine of theta half, and the modulus beta is, for instance, sine of theta half, which means that I can always say that alpha is of the form some phase factor times cosine of alpha of theta 2, and beta is another phase times sine of theta half. So that's another way to encode the same information about these complex coefficients. And so now if I rewrite my wave vector as so in this new notation, and I factor the phi phase in front, I obtain cosine theta half 0 plus exponentials of I theta beta minus phi alpha times sine theta half 1. So here, this is just a small manipulation, and you're going to understand why I'm going at such great depth to introduce this notation, is that now so let's see what we have. Now I could give a name to this phase difference here. I could call it phi, like that. And I will shortly tell you that we don't really care about this phase. And this is something you can remember. Here, phases in front of a vector phi, we don't really care. In other words, if I define a vector psi prime, which is exponential of I phi times another vector, then for all practical purposes, these two states are the same. What it means is that whatever I do, whatever physical measurement I do on psi prime or psi, I won't make a difference. So that's why here I'm going to shock you by getting rid of this factor here, because I don't care about it. But now, as you can see here, I started with 2 complex numbers, so 4 real numbers, and now I only have 2 real numbers. And in fact, it's easy to show that these real numbers are bounded, so because of the properties, the periodicity properties of cosine and the complex exponential. And therefore, I can really interpret them as angle. And as you all know from kindergarten, if I have 2 angles here, they're enough for me as coordinates of points on a sphere. And so I'm going to actually interpret my states here and put them on a sphere. Or here, this is the x-axis. This is here the y-axis. This is the z-axis. And now the spherical coordinates are defined as usual. So here I have an angle theta. And if I project on the equator plane like that, then I'm going to define phi in this way. So essentially, phi and theta that I obtained by the strategy that I just explained allow me to identify a single point on this sphere, which is called the Bloch sphere. And why we like to use this representation is that now we can think of any single qubit state as a point on this sphere. And the whole game of quantum computing, at least if I have a single qubit, which is not that interesting, but I'll come to more qubits later, is to move this point along the sphere. So a quantum computation is just moving around this point on the sphere. And this is what quantum gates do. Now, and just so since we have mathematicians in the room, here there's still this factor here that I got rid of, which means that we have weird properties. It's not a one-to-one mapping. So in other words, for instance, if you can check what happens if you do a 2 pi rotation on this sphere. You don't really come back to the origin. So that's a bit of a strange property of this Bloch sphere. OK, so now it turns out that we have a dictionary of gates, what we call gates, which are essentially rotations on this Bloch sphere. And I'm going to introduce a couple of them. So first, it turns out that these operations here are also gates. And in fact, usually when they're gates, we give them a different name, which is actually going to be the name I'm going to use. So we call it big Z, big X, or big Y for ease of notation. And so if you look at what these gates do, actually we can try to do it for one example. So let's see, if I take X applied to alpha 0 plus beta 1, you see what it does. So you obtain by linearity this, which is alpha 1 plus beta 0. So can someone tell me where this? So if I started with a point here, so if my psi was here, where does it end up if I apply X to it? If we do the anybody has an idea? What happened? Anybody wants to give it a try?
I think that the x make confusion between the coordinates and the operator.
Yeah. Well, but that's, I agree. I agree. So now I have just switched the positions of 1 and 0. So maybe something we can try to do before going to this complicated example is say, so here this is any state I can put on the sphere, but now let's try to put states that we know about. So for instance, let's try to put state 0. So where is state 0 on this sphere? So you can see here that if I want to have state 0, I need theta to be 0. So that means I'm somewhere on this axis. And then what else do I need? Well, that's it. In fact, if phi is 0, I'm done, right? It's this point here. Okay, so 0 is here. So now where is 1? So 1, if I want to get 1, then I need here theta to be equal to pi, and that means that I'm essentially here. So here the North Pole and the South Pole are essentially 0 and 1. And you notice something is that what happens if I want to do the scalar product of 0 and 1? What do you think it is? It's supposed to be 0, right? Because they're orthogonal states. It's a Hermitian operator. Sigma z is Hermitian operator, so the eigenvectors are orthogonal, so this has to be 0. But now, are these two states orthogonal on the block sphere? Not really, because as I told you, it's a bit of a strange representation. So just to be careful, here they're not, they look like they're collinear on the block sphere, but they're still orthogonal states. But now it can be, so now I guess it should be easy to see that what happens if you apply x to 0, you end up in 1. So you see you essentially do a rotation of pi to here. And so for this point here, what will happen is that you will end up, so this is x times psi, okay? So it's very easy to do these operations, and we could play the same game with z and x. And in fact, we can do any rotation on the block sphere with a very easy formula, which is given by that, and these we call rotation gates. So I'm going to call r alpha of theta exponential of minus I theta half times sigma alpha, where alpha can be x, y, or z. And my claim here is that this exponential of a matrix actually does a rotation by angle theta around axis alpha. Okay? And something that is very easy to show by using the fact that alpha squared is identity. If you write the series, the power series for the exponential, you'll see that you obtain cosine theta half times identity minus I times sinus theta half times sigma alpha. Right? So that's a very easy identity to see. And so in particular, you can see that we can recover. So how do we recover, for instance? So for instance, can we recover a given, so for instance, the z rotation, what would it be? So for instance, let's do rz of theta. If I use this here, you see that I have cosine theta half minus I theta sine theta half, 0, 0, and here cosine theta half and plus I sine theta half, if I didn't make any mistakes, which in other words is exponential of minus I theta half and exponentials of I theta half. So that's a way to get the matrix corresponding to a rotation along the z-axis. Yes?
What is their hats on the sigma?
Okay, I'm going to drop the hats. So traditionally, we put hats when it's operators, and we don't put hats when it's not, but I'm not going to put any hats today. And so now, can you see which theta I should put? If I want to find a gate which is quite similar to Z. So anybody wants to try? So there's a theta here that I could put here, so that my gate looks very similar to sigma Z. Or in other words, you see, I want a gate here, R theta, which is very similar to sigma Z. So I need to cancel the cosine. So what happens if I put, for instance, theta equals pi? I guess it should do the job, right? That then I obtain that Rz of pi is 0 minus I sigma Z. And why is minus I sigma Z essentially the same as sigma Z? Is for this global phase issue that I already mentioned. So they're equivalent up to a global phase. So the states we will get are the same. So essentially, you can think of Z here as a pi rotation along the Z axis. Same thing for X along the X axis, and for Y along the Y axis. And so all these are ways to think about qubits, how to move along the Bloch sphere, and basically you can write any operation on the Bloch sphere with these rotations, as you can be convinced, right, that by moving with rotations, I can go everywhere on this Bloch sphere. And so if you can do it on a quantum computer, then you can move everywhere you want on the Bloch sphere. Okay? Any question up to now? And this is essentially what we'll be using a lot in the remainder of the lecture. Okay, so now we know how to manipulate a single qubit, and we're going to manipulate 2 qubits. Oops. So now that was 1 qubit, and now let's move to 2 qubits. So as Maziar told me, so when I work now with multiple qubits, so instead of working in a two-level system, which we usually call a H2, so it's a 2-level system, now our Hilbert space is going to be a tensor product of a lot of 2-level systems. So actually, I'm going to have small n of them. And so in particular, you see that the dimension of this vector space, of this tensor product of vector spaces, is 2 to the n. Right? It's a huge Hilbert space. And if I look at the basis, so a basis of this state, an easy basis for this state will be all the, so I'm going to give it a name. So B1, B2 tensor Bn for Bi equal 0, 1. So here, it's a very standard way to construct the basis of a tensor product. I just do a tensor product of the elements, the individual basis elements. And this is something that we call usually computational basis. And in the rest, I'm going to be sloppy with notation, which is that, for instance, if I look at the case n equals 2 qubits, the basis is usually, if I write it in full, 0, 0, 0, 1, 1, 0, and 1, 1. But I'm going to be sloppy and call it instead 0, 0, 0, 1, 1, 0, and 1, 1. Okay, so I'm going to drop the tensor products. And of course, if you have questions and I'm too fast with the notations, ask me also. And so you see, of course, now I have 4 states. So it means that any state, psi of 2 qubits, can be written as alpha of 0, 0, plus beta of 0, 1, plus gamma of 1, 0, plus delta of 1, 1. So you see, I need 4 complex coefficients now to describe a state of 2 qubits. And that's one of the reasons why people say that quantum computers are very efficient, is that you can store 2n complex coefficients in a wave function on n qubits. So that's a lot of coefficients. And so that's why people say that if you store the answer of your computation in the wave function, you have a lot of information in n qubits. But we'll see that it's a bit of a wrong statement later, okay? Because you need to extract information from this wave function. But nevertheless, that's very important. And now there's a notion also that is very important, is the notion of entanglement, that I'm not going to cover too much, but still it's important that you have this notion in mind. Entanglement is essentially the difference between defining a tensor product and a Cartesian product, like Maziar said. So you see here, this is really different from doing H2. Okay, it's a very different mathematical space. And essentially, entanglement is defined by what a non-entangled state or a factorized state is. So factorized state means not entangled, is defined as a state that can be written as a tensor product of one qubit state, so phi1 tensor phi2 tensor phi n. So that would be a factorized state, or also called a product state, or not entangled state. And it reads like this, and you can see it's very different from a generic state. And one simple way to see it is to count the number of numbers I need to describe this state. And you see here that for this state, I need alpha 1, beta 1. For this state, I need alpha 2, beta 2. For this one, alpha n, beta n. So the total number of coefficients I need is 2 times n complex coefficients. If I don't discuss the normalization conditions. So you see, you go from, if you have no entanglement in your system, your wave function contains an information which is just 2 times n coefficients and not 2 to the n. And of course, if you have a quantum computer which has no entanglement, it means you can describe its wave function only with 2 times n complex coefficients, so you'd better do it on a classical computer. So you really need to have entanglement for a quantum computer to be interesting. And now, in the same way we have gates to move around the block sphere for single qubits, we also have gates to create entangled states, to move in the big Hilbert space. And it turns out that I'm not going to describe gates for 2, 3, 4, not because it would be too long, but because we need only to have 2 qubit gates and a certain class of 1 qubit gates to achieve any transformation on the n qubit Hilbert space. So that's why I'm going to stop at 2. And usually people in hardware also stop at 2 because physically it's easier to do 2 qubit gates and 1 qubit gates than more. Although some platforms can achieve n qubit gates in one go, like trapped ions, for instance. But today I'm going to focus mostly on 2 qubit gates. And so probably the most famous 2 qubit gate is called the C0 gate. It's famous because, in fact, it comes from the classical world. It's called C0 for controlled not. And controlled not means that it's going to work in the following way. So C0 acting on state 0, 1, the way it works when you have a controlled gate is that you look at the value of the first qubit, which is called the control qubit here. If it's 0, then you don't do anything. That's the definition of what a control is. Now, if you do control not, say, on 1, 1, then you look at the value, it's 1, so you do something, and what you do is actually the operation that is after the C. So what you do is you do 1, and then you do not applied on 1, so not in classical logic, which is also, by the way, what we called X before. So that's why you will also see notation that is Cx, that this control not gate is Cx. And then you end up with 1, 0. So that's the way this gate works. And I can summarize it by looking at its matrix. So the unitary corresponding to, so let me walk you slowly. So here I'm just writing what happens. So 0, 0. When you apply C0 on it, it doesn't change. So you put a 1 here, 0, 1, same thing. And then here you have control qubits which are 1, so you need to flip the bit. So 1, 0 becomes 1, 1, and 1, 1 becomes 1, 0, like that. Okay? And here I took care to enumerate the bases because I could have chosen another ordering for the bases. So here I really choose this lexicographical ordering of the bit strings. But I could have chosen another. So I could have chosen to order my bases 0, 0, 1, 0, 0, 1, 1, 1. I could have also chosen that if I had in mind that my binary representation has the most significant bit on the right. Okay, but here I choose my most significant bit to be on the left, which is a usual convention. But as we will see when we tackle the Fourier transform, it plays an important role to have these in mind. Okay, I could also have used the gray code or whatever, but here this is typically people use this here. Okay, so that's C0, and it's very famous, and it has a special symbol, which is going to be a good occasion for me to tell you that to write a quantum program, we're going to write it as a sequence of these operations, of these gates, which are going to move me through the Hilbert space. And the notation is usually it's like a score in music, where each qubit has a line. And when you modify a qubit with a single qubit gate, you draw a box. And then you write the symbol of this gate. So for instance, for an X gate, so sigma X, you write it like this. If you modify the first qubit, then that's what happens. Now, if you want to modify the second qubit with, let's say, R X of pi half rotation, then you write it like that. And now a C0 gate is going to be written as with this symbol. So this dot here is for the control, and here this is for the not. Okay, so this is the way this gate is written. And let me also introduce you to the fact that we can have controlled rotations, controlled gates of any kind. So I have control U here, which is a gate which is controlled and unitary. So in other words, the way that this CU gate works is that if I do CU, for instance, of 1 times 0, then I obtain 1 times U applied to 0. That's the definition of these controlled gates. And now if I write the matrix of this gate, control U, still in the same basis, you can easily see that the first two states which have 0 on the control are unchanged. And then the other states are changed according to the unitary matrix describing U. Okay, so you can have that in mind. Another way to write this, which can be useful when you do a computation, is to write it in a notation that I will probably need to explain, which is a ket and bra notation, which physicists like a lot. So let me explain. So first, what we can see is that control U is an operator. And now we need to check that the right-hand side is also an operator. So it's a tensor product. It's a sum of tensor products of stuff. And the stuff in the tensor product is identity and U, which are operators. So now what I need to convince you of is that this is also an operator. And here you can check that, OK, this is something I didn't really define, but we think of these kets as column vectors, and of these bras here as a transpose conjugate. And so when you do a transpose conjugate, you turn a column vector into a line, so that here you really have to think of 0, 0 as column vector corresponding to the first vector in my basis. So it's 1, 0 times the transpose conjugate. Here I don't have to conjugate anything. So it really corresponds to this matrix here. Okay? And now to make the proper connection, to explain to you how this operator acts on matrices, let's move to... Will I be able to recover this table once I send it? Oh, nice. Okay, so now let me tell you a bit more what this cross operator means. So if I do A tensor B for two matrices, let's say A, B, C, D times B, then so in math, sometimes this is called a Kronecker symbol or Kronecker multiplication. And the way you construct the matrix here is the following. You do A times matrix B, then B times matrix big B, C times B, and D times B. So that's the way these computations work. And we can try that it works for what I told you here. I hope it works. So if I do CU, and I say it's 0, 0. So 0, 0 we said was 1, 0 cross identity plus. So now we have 1, 1 and 1, 1. I can convince you easily by the same computation. I will get 0, 0, 0, 1 cross U. So let's see if it works. If I use my notation here. So 1, 0 times 1 is going to be essentially 1, 0, 0, 0 plus 0, 0, 0 times 1. So big 0, big 0, big 0 times U. And so you see that it works. Okay? So this is how you write the matrix of a controlled operation. And you can check that for C naught it works, right? You see that it's identity here, and what is this matrix here? It's X, right? I told you it was controlled X. So it all falls into place. So these are my 2-qubit. So this is one example of 2-qubit operation. And actually a lot of the operations we're going to see in the lecture look like control something. And in fact, another gate I didn't really tell you about, I didn't tell you at all about, is the phase gate. It's a 1-qubit gate. And this definition is 1, an exponential of minus of plus I theta. That's another gate. And in fact, the reason why I didn't introduce it is that it's the same as one of the gates we already mentioned. Maybe you can tell me. So among all the gates we saw in the single qubit gates, there is one gate which I claim is the same as this phase gate. So you see, this phase gate is diagonal, so we need to look for a diagonal gate. So what is the diagonal gate we saw? Yes? Yes. So we saw that rotation along Z was exponential of minus I theta, exponential of I theta. So how do you make the connection between those two gates? So what you can do is factor out a phase factor like that. And then you get 1, 0, 0. And here exponential of 2I theta. So you see that it's same as, and so I miss factors of 2 that I had above here. And now you see that it works. So now you see that both gates, RZ theta and P theta, are related by a global phase, so I don't care about the global phase. Okay? So that's a gate we'll use a lot in the Fourier transform. So let me check if I forgot important gates. So I think we're good. Okay, if you want, I can introduce one more for cultural reasons, but I won't use it too much. It's a Toffoli gate. So Toffoli gate is a 3-qubit gate whose diagram is like this. It's called Toffoli. And it's actually a control not gate. It's really the same as control not. And it's used a lot in classical logic, and therefore also in quantum computing, because there's a lot of classical circuits that are used in, for instance, to do additions in classical logic, which can be reused in quantum computing. So you will see this gate a lot. Okay, and so now it looks that we can do a quantum computation very easily. We just put those gates in sequence and with this notation here. And so this notation here as a musical score is called a quantum circuit. So quantum circuit is the sequence of those gates. And now it looks like it's very powerful because at the end, of this operation, I will get a vector which has 2 to the n complex coefficients, which I cannot really represent on a classical computer. And maybe you have an idea today of what is the n, which is the maximum number of qubits that I can store on a classical computer on the biggest computers today. Any guess? If I want to store 2 to the n complex numbers, how large an n can I have? Yeah, Igor apparently has the answer. No, 30. I mean, on your laptop you can, but on a big machine, like a HPC machine. So just to give you an order of magnitude, what is 2 to the 10 complex numbers? If I'm not mistaken, 2 to the 10 is 1 kilo, but then a complex number should be 16 bytes. So it's 16 kilobytes. So 2 to the 20 will be, so the next after kilo is mega. Then 2 to the 30 is gigabytes. And if I do 2 to the 40, then I get terabytes. And so 20, 30 terabytes is essentially the best one can do on today's classical computers. So that means that today we can basically do quantum computations in a perfect way on a classical computer if we have enough terabytes. Okay? But that means that if I want to do something powerful, probably with a quantum computer, I need to go to more than 40 qubits. Now, I want to add a small caveat here, because now you'll accuse me of being a physicist and talk to you only about entanglement, but it turns out that there are also circuits which have thousands of qubits which you can nevertheless simulate classically. Well, first, circuits which have only 1 qubit gates, because if you have only 1 qubit gates, you produce only factorized state, only product state, so you need only 2 times n complex numbers. So essentially single qubit gates only. Only then easy for classical computers because it's only 2 times n complex numbers. Now there's another class of circuits which is very easy to do on classical computers is quantum circuits with gates which are called Clifford gates. So Clifford gates is a particular class of gates which is easy to do on classical computers. And yeah, so essentially the storage cost of this, I'm not going to go into too much details, is proportional to n squared. So you see, instead of 2 to the n, now if you have circuits which have only Clifford gates, and Clifford gates, to give you concrete ideas, are essentially, for instance, if you have only x, y, z, c naught gates, for instance, in your circuit, if you have only those gates, then there's a clever way to store the state in only n squared numbers. Okay? Yes. So essentially, to give you, since we introduced the block sphere, essentially what these Clifford gates correspond to are pi over 2 rotations. So if you have a circuit that has only pi over 2 rotations or multiples of pi over 2, it's very easy to store the information on a quantum computer, on a classical computer. And perhaps the intuition is that if you do only pi over 2 rotations, the only points that you can reach in the block sphere are very special points that you can describe in an easy way, economical way on a classical computer. Of course, it's easy. It's harder to do the statement on more qubits, but it's roughly the idea. So it means that if you want to do something powerful, the ingredients you need is entanglement. Otherwise, it's easy. That's this first case. And you need gates which are beyond the Clifford gate set. And one surprising result is that if you add a gate which is called the T gate, which is essentially the phase gate with pi over 4. So if I'm not mistaken, it's 1, and so exponentials of I by 4 like that. So if you have a gate called the T gate, which is essentially it's a z rotation of angle pi, quarter pi. So it's not a pi multiple of pi half. Then it's enough to have Clifford gates and a polynomial number of T gates, to do any single qubit rotation and therefore also any unitary. Okay? And that's it can be quite shocking that with only pi4 rotations you can synthesize any rotation with an arbitrary angle, but there are relations that tell you that I think you can do any irrational angle with a combination of these T gates and some pi half rotations. And since irrationals are dense in floating point numbers, it's more or less the reason. Okay, but I shouldn't make two mathematical statements here because I see Laurent frowning. Okay? And actually the reason why I wanted to mention briefly this gate is that when you do quantum error correction, it's quite convenient to write your circuit in terms of Clifford plus T gate set and get rid of arbitrary rotations. Because then it's easy to do quantum error correction on these Clifford gates, and T gates are a bit more complicated, and Maziar didn't really have time to talk about T gate factories and all this business, but this is what is behind this decomposition. But since my focus is going to be mostly near-term computing, I'm not going to mention too much these Clifford gates, but you can keep that in mind. All right. Any question? Okay. So now, what we're going to do is actually now learn a first small quantum circuit that is going to be useful in the remainder of the presentation if we want to do a quantum Fourier transform. Because the goal of today's lecture is to reach to the point where we can do a Fourier transform on a quantum computer, and if I have time, also to compute the lowest eigenvalue of a Hamiltonian with this Fourier transform. So let's see. Now let's look at a very simple circuit. So I'm going to introduce yet another important gate that I didn't introduce yet, which is called the Hadamard gate, which is such that, so its symbol is H, and its unitary, if I write the corresponding matrix, is 1 over square root 2, 1 over square root 2, 1 over square root 2, and minus 1 over square root 2. So in other words, if I do UH applied on state 0, I get 0 plus 1 over square root 2. And if I apply it to 1, I get 0 minus 1 over square root 2. So you see it's an important gate because it creates a superposition state, which is something you couldn't do on a classical computer. And by the way, Hadamard is also part of the Clifford gate set. Okay? So, and this gate is important because it can allow me to create a state that you probably have heard of. So, and probably it's the first exercise we're going to do together. So let's say I have a circuit with a Hadamard gate and a CNOT gate, and I would like you to tell me what is the output state of this circuit. And since it's the first we are looking at together, we can do it together. So let's look at what I do if I do UH applied to 0, 0. Then what I get is that if I decompose carefully, it means I apply UH to first state 0, tensor 0. I leave the other guy alone. So I get 0 plus 1 over square root 2 times 0. So that's the first step. So after the first gate, that's the state I get. And then when I do C0, so U of C0 times UH times 0, 0, then I need to be careful. So now I need to use linearity. So I do U of C0 times 0, 0 plus U of C0 times 1, 0 over square root 2. And so you see, now I do U of C0 on 0, 0 is nothing because the control bit is 0, so I get 0, 0. And then U of C0 on 1, 0, since my control bit is 1, I flip the second bit, so I get 1, 1. And I get a state which physicists like a lot because they can get Nobel Prizes with it. It's called the Bell state. And why am I mentioning Nobel Prizes? Because with this state, you can create you can prove interesting inequalities called Bell inequalities that gave not Serge Laroche, Serge Laroche was for another thing, Alain Aspect the Nobel Prize a couple of years ago. Okay? And so you see here that with this simple circuit, I can create a belt state. And the reason why I want to mention it is that we're going to look at an extension of this belt state, of this circuit, to so it's an interesting permutation problem. Okay. And now we're going to use it to write a slightly more complicated circuit that is going to be a very important building block for the rest. Okay, so now let me take a slightly more complicated example where I put the initial state in state j, where j can be 0 or 1, and I now put it into a Hadamard gate, and I would like you to give me the expression of the outgoing state as a function of j. So if we do it together, you see that if applies to 0 is 0 plus 1 over square root 2. If I do apply to 1, then I get 0 minus 1. So if I want to have a nice expression for this, you see that it's always 0, then it's plus, and then I could write it as I pi times j times 1 over 2, right? It's a bit a strange way to write it, but you'll see why I use this way. So expression of I pi is minus 1, so you see that it should work. And now I'm going to introduce a notation that I'm going to be needing for the rest, which is the binary fraction representation. So binary fraction is very simple. If I write 0 dot j1, j2, j3, it means j1 divided by 2 plus j2 divided by 4 plus j3 divided by 8, etc., etc. And so now I want to use this notation in this circuit. And so you see, if I don't make any mistakes, that this should be 0 plus exponential of 2I pi times 0 dot j times 1. Okay? Okay, it's a strange way of writing stuff, but you see it will be useful later. Okay, and now I'm going to use another circuit, a slightly different circuit, which will be a very important building block. And essentially, once you know this circuit, you can do a Fourier transform. And this circuit is the following. We're going to make it simple first. So 0, Hadamard. And let me check here. I'm going to do a controlled phase gate here. And I'm going to put a state j here. And I want to find the output state. So let's see. Now, if I do things carefully, then I do so controlled phase times UH times 0, 0 times j. Sorry, times 0 times j. Then what it means, what it gives me is control phase. Then 0 plus 1 square root 2 times j. And then here's what the control phase does. For this first 0, it doesn't do anything. And for when it's 1, control bit is 1, then I apply the phase to the second qubit. So it means that I get 0 plus the phase, control phase. So now I need to apply phase of theta to j. Okay, what is phase of theta applied on j? Let's do it here in the small corner. So you remember that phase of theta is 1 exponential of I theta. So if I do phase theta on 0, nothing happens. And if I do phase of theta on 1, I get EI theta. So you should agree with me that if I do phase of theta on j, I get EI theta j times j, right? Is it fine with you? It could be not fine. I mean, I could make mistakes on the board, so please check that you agree, okay? That if you applied, okay, everybody is okay with that? So now what I end up with is exponential of I theta j times 1, okay, times 1 over square root 2 times j. So you see it's a bit of a strange example because the output state, so is the output state entangled or not? If you look at this state straight in the eye, is it entangled or not? I mean, should it be entangled? When we look at the circuit, it has 2 qubit gates, so it should be entangled, but is it? It's separable, right? So, I mean, I didn't write it, but I could write here that it's tensor j. So, and that's why I'm going to write the result on the circuit here as here I have j, and here I now have a state which is 0 plus exponential of I theta j 1 over square root 2. So this circuit is very nice because what it does is that it has some information here. So the information is this bit j 0 or 1. And it transfers this information on the other qubit here in the dephasing between the 0 and the 1. So it's very convenient to have such a gate, to have such a construction. And the name of this is, it's a phase kickback circuit. And why is it called phase kickback? It's because the phase here of the operator here is kicked back on the first qubit. So it's a very important building block. And now we're going to do a last exercise before we actually do a Fourier transform. Is that we're going to look at a slightly more difficult circuit. And this slightly more difficult circuit is this one. I put J1 here, J2 here. I put a Hadamard gate. And I put a control phase gate. But this time I put a control phase gate of pi half. And now I want to know what's happening next. So let's see. There's one part I can do easily, and which I could have commented on here. You see that here J is an eigenvector for phi, and that's why it goes through, and it stays here. So you see here that I can put J2 right away here. But now the hard part is what happens to this. And so now maybe I can be tough and give you the result without doing the full derivation. And that's actually what I'm going to do. What we get here is 0 plus exponential of 2i pi times 0 dot j1, j2 times 1 divided by square root 2. So, and maybe I'll leave it as an exercise so that you make sure in the afternoon that you have understood what happened here. If you have time in the afternoon, but you won't have time. But believe me that this works. And as a reminder, this 0.j1, j2 really means j1 plus j2, 4. Okay? And you can check that this works. That essentially, now we have a box which is such that if you have j1 and j2 as the entry for this circuit and a pi-half rotation, you'll get here the binary fraction corresponding to j1, j2 in the phase here. And it's pretty nice. So another way to see things is that when you go through the Hadamard gate, the j1 is going to get to appear here because of that. And here the pi-half, the role of the pi-half here is to divide by one more factor of 4 to get you to second position here. Okay? So essentially the rotation here angle plays the role of where you put the j2, and the role of h is to put the j1 just after that. And so in such a way that you can think of these building blocks really as ways to encode the binary information of your input register into the phase here. Now, why do we like to do that? You probably, if you did physics at some point in your studies, you heard about interferometry or interferometers, which is usually something that people hate when we do it, interferometry. But what is the role of interferometry is to find the phase of something, the dephasing between two rays of light, for instance. And essentially, all we're going to do with fault-tolerant quantum computers is essentially an interferometry experiment. And I'm going to be a bit more specific. But for that, I might do a bit of a detour through an example that you probably have heard of, which is Young slits. So you probably have seen this at some point, that if you put light, coherent light, so with the same frequency here, and you shine it on you shine it here on a board with two slits, and you look at the pattern of light here, what you're going to see is a nice cosine. And you're going to have here what we call an interference pattern. And the interference pattern is going to measure essentially the dephasing here, exponential of I phi, between the two rays of light. I'm not going to enter into too much details. If you don't know about this example, forget about it. If you know, then it's a refresher about good old physics. So here, essentially, the frequency of the oscillation you see on the board here is related to the dephasing, and the dephasing itself is linked to the distance between the two slits. So physicists like to use it because if they want to determine A, then they look at this the oscillation on the board here. And in fact, what I'm going to argue is that what we're doing here is exactly what we're doing there. So, but for this we need one more thing, is the fact that mathematically here, if I call x this axis, and I call t of x the transmission of this board. So in other words, if I write on this axis x, and I write t of x here, then a slit is essentially an opening here. Okay, I should write it like a delta function for the first here, then a delta function here, a longer. So essentially, this is what I call the transmission function of this board. And what we read off here is essentially the Fourier transform t hat of k of this transmission function. So Fourier transform of t of x. This is what interferometry experiments do. They take a given pattern here, they do the Fourier transform, and that's what you read here. Okay? And essentially, my claim is that we can do the same thing with this circuit. Why? Because here what we do, and I'm going to study a slight generalization of this, I'm going to take a circuit here, H, and I'm going to put here a unitary here, and input here a vector phi, which is supposed to be the eigenvector, one eigenvector of U. Okay? So, which, by the way, falls into this case here, right? Because J here was an eigenvector of phi. So, and I'm going to suppose that U times phi is of the form ei phi times psi. Okay? And why can I write it in this form is because unitary operators have eigenvalues of this form. And so now if you check, what happens here is that if I do that, here it's like if I start with one ray of light, 0. The Hadamard gate is going to split it in two. You're going to have here on this register 0 plus 1. I don't put the square root of 2, but it's there. So I have 0 plus 1. So it's like if I started with 0 here, then just after the slit, I have 0 plus 1. So I have two rays of light. And then what the control unitary is going to do is that it's going to transform it into 0 plus exponential of I phi times 1, right? Because 0, you don't do anything, and 1, you apply the gate. And now it's not exactly enough. Once I'm there, I have a dephased signal, but now I need to do the Fourier transform to read it here, to read off the result. And in fact, the Fourier transform for 1 qubit is also a Hadamard gate. And so let's check that I'm not leading you up the garden path. So let's see what happens when you apply h to the final state. So if you do UH applied to 0 plus EI phi, and I don't put the normalization factors, then you can see that I'm going to factor out 0 of 1 plus EI phi plus 1, and I'm going to put a sign proportional to, because I forget all the square root factors. Do you agree with that? So h applied on 0 is 0 plus 1, and h applied on 1 is 0 minus 1. That's why I get a plus sign here and a minus sign here. Okay, that's it. And now I can always also factor out a cosine, a phase factor, sorry. So let's say like that. If I factor exponential of I phi half, then I get 0. Then I get, so if I'm not mistaken, a cosine phi half, 0, and here minus I sine of phi half, if I make no mistakes, which can be possible. Yeah. And there's factors of 2 everywhere that I forget, but you should be convinced by that. And now I'm going to use a result that Maziar used, is that now I want to measure this qubit. So I'm going to put a measure symbol here. And measuring allows me to write that the probability of getting 0 is given by a rule that is called Born's rule, that essentially tells me I should do 0 and the final state, so psi final, and take the squared modulus. So this is the rule. The probability of getting 0 is given by this. So you see it's a line vector applied to a column vector, so it is a number, so it makes sense. And you can check that if you do that. So if I apply, so now I'm going to do something I shouldn't do, but so I'm going to multiply on the left by 0. You see, I apply it to, so bra 0 times ket 0 is 1, and bra 0 times ket 1 is 0. So the second term goes away. So the only terms that remains is cosine. So what I get is cosine squared of psi theta, of theta half, okay? And so now you could see that this is essentially this cosine that I was talking about. So here, this simple circuit allows you to get access to phi. Now there's one catch, which is precisely what the Fourier transform is going to help me doing if I want to generalize the trick. How do I get access to P0 in practice? What is in practice so if I give you access to a quantum computer, is it enough for you to do one call to the quantum computer and measure the qubit? No, because you're to get 1 bit of information, 0 or 1. So if you want to get the probability of 0, you need to measure the frequency of zeros appearing if you do 100 times the experiment, for instance. So the price to pay the price to pay here is that if you, so let's say you measure, you have n repetitions, then you obtain the frequency f of 0 appearing. So it's different from p equals 0, right? From p of 0, but it's, so if I write it in sloppy way, it's p0 plus an error, epsilon. And this error epsilon, you will agree with me, with central limit theorem, is going to be 1 over square root n. So it means that the total runtime, and promise you I won't use too much the bottom of the board, but okay, runtime of my algorithm is going to be proportional to the number of repetitions. And this is 1 over epsilon squared. So if I want to reach a given accuracy on my phase, which, by the way, is the sine or cosine, so I don't really have the phase, but OK, I could also measure other information to get exactly the sign of the phase. But so this is more of a detail here. But so essentially, if I get access to P0, I have access to phi. But the number of repetitions I need to do is 1 over epsilon squared, which is a lot of repetitions. In fact, this is a statistical uncertainty, right? So I'm not really using my quantum computer the way I should if I do that. I'm paying classical Monte Carlo price when I do that. And what we're going to see next is how to actually reduce this 1 over epsilon squared to 1 over epsilon, which is the best one can do because we have a quantum computer. Okay? But essentially, here I've introduced a circuit that does essentially textbook quantum mechanics 101, but with a quantum circuit. Okay? Any question to this point? So now we have the building blocks to do Fourier transforms and then the phase estimation that I was mentioning. And please tell me if I write too small. I can try to, because I see that as I go, maybe my writing is getting smaller and smaller, and maybe more slanted than so. Okay. So now we want to do a Fourier transform. And the reason why we want to do a Fourier transform is that here in our experiment, in the interferometry experiment that I just showed you, we need to do Fourier transform to get the interferometry pattern. That's the inspiration for doing so. OK. So what is a Fourier transform? So what I'm going to assume is that I have access to a signal of size big N, which has coordinates xj, so with j going from 0 to n minus 1. So this is my signal, xj. It's a big vector of size n. And so this is the input, and the output is going to be also a signal, but now that I call yk, also with k from 0 to n minus 1. So I'm going to do a discrete Fourier transform. So it's a DFT that I'm doing. And the formula that you probably know is that for all k, I have y of k, which is 1 over square root n, sum over j, from 0 to n minus 1 of exponential of 2I pi of j times k, divided by n times xj. So that's what I want to achieve when I want to do a Fourier transform. And here it's just the definition of the discrete Fourier transform. And now it turns out I want to do it on a quantum computer. And the game I'm going to play is to say that I start with a psi input state where I'm going to encode the signal. So I'm going to say that my signal here is a superposition of states computational basis state j, and the amplitudes, what we call the amplitudes, the coefficients, the complex coefficients, are going to be the xj's. And here, I'm going to also say that big N is also 2 to the power n, so that here my j goes to 2 to the n, minus 1. And the game now is to say that I want to find a circuit such that the outgoing state is sum over k from 0 to 2n minus 1 of ykk. That's the game I want to play now. OK, do we agree on the game we want to play? There's something you should not be happy about? That there's a condition of wave functions that I need to make sure of, is that in principle my wave function should be normalized. So in principle, I'm going to pick signals such that sum over j squared equals 1. OK? And same thing for the output. But that's a condition that's not a big issue. But just to remind you. OK, so that's the game I want to play. And the nice thing about quantum mechanics is that, as Mazia showed you, it's driven by a linear equation, which is the Schrödinger equation. So I don't need, if I want to show a result, I need to show it only on one arbitrary computational basis, and then it will be fine, because by linearity it will work also. So what I'm going to do is the following. I'm going to say I'm starting with psi in is going to be a particular j that I can call j star if you want. Although at some point I might drop the j star, but it's a computational basis state. And I want to see what happens when I apply the formula to this. So in other words, if I have psi in equals psi j, I want to understand what is psi out. So psi out, as I said, so that's what I require, is sum over k of yk times k. But what is yk? So yk is 1 over square root of 2 to the n times sum over. OK, so now that's when I am going to use the simplification. Do I need the sum over j? OK, let's do it carefully. So sum over j of exponential of I pi over 2n times j times k times xj. So that's just a formula. I just expanded the formula that I just wrote here. But now there's something special about my signal, right? That my signal is just one state. So it means, in other words, that xj star equals 1 and x of j different from j star equals 0. Okay? So in other words, I can simplify this sum here with exponential of I pi over 2n times j star times k. Okay? So the sum goes away. Are you happy that it goes away? Because otherwise it would have been complicated, right? So now I have only, so I end up with a sum over k. And I'm going to put the square root factor in front of exponential of 2I pi over 2n jk k. OK, and now it looks a bit hopeless. But that's when we have to remember something. Now what I'm going to do is to say the following thing. I'm going to say that j is an integer, but here, remember what j means here. In fact, it really means j1, tensor j2, tensor jn, right? I have n qubits. So what this j means, and actually you could have shouted at this point that you don't understand what this j means, right? Because j is an integer, but what is the link with my tensor structure? Well, that's the link. That, in fact, what I call j here is, in fact, tensor product of j1, where j1, j2 correspond to the bits in a binary decomposition of j. And the trick I'm going to play, which is a bit subtle, is that I'm going to use a different binary decomposition for j and for k, for reasons that you will see later. So j I'm going to decompose as, so that's when, so j1 2 to the n minus 1 plus j2 2 to the n minus 2 plus jn. In other words, I'm going to choose the first bit to be the most significant one. So which I can also write sum for of p, jp, p equals 1 to n of 2 to the n minus p. And now what is a bit strange is that I'm going to use a different definition binary decomposition for k, which is going to be j1 plus j2 times 2 plus jn times 2 to the n minus 1. Why not? I can always choose to do that. Sorry, k. Thanks. So k1, k2, kn. And so now I have sum over q from 1 to n of k q of 2 to the q minus 1, if I don't make any mistakes. Okay? And okay, now that's where I started dropping the j star. So now I'm going to call j equals j star because I don't want to carry all the j stars on my bits, right? So you have just to remember that j is a particular j, it's not any j. And now, what is kj? What is jk? And bear with me, you're going to see why I'm doing all these tricks. So it's sum over pq, and I'm going to keep pq separate for now, of jp kq 2 to the power n plus q minus p minus 1. Okay. And the reason why I want to do all this is also that I want to divide by 2 to the n, because you see here in my exponential here, I have 2i pi and then divided by 2n, and that's the 2n that I put here. And the 2n is going to remove this n here, okay? And why do I want to do that is that if you look carefully at this power of n, depending on whether the exponent is larger or smaller than 1, you're going to have an integer or not. And you see that here, if you have exponential of 2i pi times an integer, then it's 1. So I'm going to separate the integer part of this sum from the non-integer part. Okay? So let's do it. So that's where it becomes tricky. But I should get some help from you guys. So now q, I want q minus p minus 1 to be larger or equal to 0, right? So I want q to be larger than p plus 1. P plus 1 until n. So I'm going to cut so q smaller than p plus 1. And then I keep jk, jp, kq 2 to the q minus p minus 1. And so do you agree with me that now, in all the rest, I'm going to be able to remove this part, right? I mean, I'm not saying that this is an equality, but when I put it in the exponential, I can remove all these terms. So in other words, now my psi out is 1 over square root 2n sum over n of k of exponential of 2i pi, oops, and then sum over p from 1 to n, and then sum over q from 0 to p of jp kq times 2 to the q minus p minus 1. And the whole thing times k. All right, so now it looks desperate, it's still desperate, but you're going to see we're going to make progress soon. You see now I have an exponential of a sum. I can turn it into the product of exponentials. And the reason why I want to turn it into product of exponentials is that here K, remember, is K1, product K2, product, and so on and so forth. So if I can make this into a product over, so Q sorry, now I'm confused. Yeah, so the Q is correct, but maybe I wanted to do the reverse trick. I think I messed up the trick. Okay. There were two ways. I chose the wrong one, but nevertheless, it's pretty easy to do it correctly. So let me not erase this, but write it in a different way. So sum over Q from 1 to n, and now I'm going to split the other sum. Because the Q's, you see, are the bits corresponding to K, so that's why I want to keep this one. So now this is sum over P plus sum over P, and I want to find that, so this is the condition for being integer. So I want P to be smaller than Q minus 1. So P smaller than Q minus 1 and P larger than Q minus 1. And so this term here should disappear. Is it, so do you agree that, so here instead of doing a decomposition on the Q index, I do it on P index. And the integer condition is the exponent should be larger than 0. So P should be smaller than Q minus 1. So I can drop this term. So now I end up with, so essentially the same thing, but now it's much better for me because I get Q from 1 to n, and then I get P from Q to n. Okay, and now I can do a product on the ends of exponential of 2i pi of sum over P Qn of J P, and the KQ can actually go in factor of all this. Okay, do you agree with that? And now I'm done because you see here I've got a big product. Okay, I can do one more thing, which is, okay, let me see if I can convince you it works this way. Okay. Please shout if you don't agree, because I'm going to do all at the same time. Yes.
In the second line,
I missed.
should be a 2 to the minus Q minus
Yeah. Yes, this one. And now I'm almost there. I'm just saying that. Okay, so I have a sum of a product, and here I have a product. So now I turned the KQ, I turned it back into in the tensor product here. And now I expanded, no, okay, that's the point, is that now I expanded the sum over K here. So now this is like KQ equals 0, and this is KQ equals 1. And now I'm good because what I have here is indeed JP 2Q minus P minus 1. Okay? Yeah. So that should be fine. Okay? And now I'm almost done. I'm going to expand it so that we take a hard look at what it looks like actually. So what is the first term? Maybe the last term first. So I'm going to look at the last term. So last term is q equals n. So if q equals n, you see here that I have only one term, which is jn, right? And jn, so I have 0 plus 1 over square root 2. And now jn is what? Exponential of 2i pi. And jn, so I have p equals q equals n, so n minus 1. So is it fine? Is it? Probably you see better than me at this point on the board. Do you agree that it's this guy, 0.1 jn? And so now, if you are convinced with that, then we should end up here in this first term as exponential of 2i pi, and then exponential of j1 to jn 1 over square root 2. You could check that it works by recurrence, okay? So if this works, I mean, then it will work here, okay? And now, so that's basically we made it to the hardest part, because now what we did is we now have shown that I'm going to do a picture actually. Now I'm going to do a picture of the corresponding circuit. Okay, so now let's do a big picture. Okay, so now we have n lines. And we start with a j, which is j1, j2, j3, and last I'm going to call jn. And what we see is here at the end, what I should get is a state. Is it entangled or not? In principle, you should be convinced that it's not, right? It's just a product of states. So it's quite surprising. You do all this work and you get only a non-entangled state. But in fact, Fourier transform doesn't entangle too much. It's not the point of Fourier transform. The point of Fourier transform is to start with a very entangled state and do something clever. But it's not creating entanglement. And then what we get is that at the end here, we get 0 plus exponential of 2i pi times 0 dot j1 jn 1, and I don't put the square root of 2. Then for the next one, it's dot j2 jn 1, and so forth. And the last one is 0 plus exponential of 2i pi of 0 dot jn plus 1. And now my claim is that you should be able to tell me what circuit, what circuit we put in the last 5 minutes, or 2 minutes. Yeah, we can do it in 2 minutes, because I believe you're very good at it. And so now let's try to fill in the blanks here in the circuit. So using the trick that we put on the board, you see the circuit with the J1, J2 top here on this board. Now let's try to use it. So how do we do it? So let's start maybe by this state. How do we put this state here? How do we collect all the phase information of the input register on this first state? Okay, so I'm just going to do the circuit. So I put Hadamard, and then I want, so Hadamard put me the J1. Then J2 means I need to take phase of pi half here, so that I get J2 afterwards. And then I do here phase of pi 4 here. And then for the last one, what do I put? 2 to the n or n minus 1? N? Okay, I believe you because my brain is completely dead. So now, that's for the first one, okay? Second one, what do we do? Well, we put Hadamard here. And now we fetch the phase for J3 here. And similar, okay? And now I want to do the last stage. And the last stage, what is it? You tell me the last gate? It's H. And that's it. So now you know how to program the Fourier transform. And I guess I'm going to stop here, and it will be a nice transition for tomorrow where we actually use this Fourier transform for something useful. So you see here this circuit, maybe one observation we can make is that it has a recursive structure. You see here, you have this block, and then this block, and then this block. That maybe the first thing I'm going to show tomorrow is that from this you can recover fast Fourier transform very easily. You can really get the algorithm in n log n just by looking at this circuit. And then we'll do something quantum about it and look at what we... So the circuit is a very long circuit if you count the number of gates. Here you have order of n gates repeated n times. So the number of gates is O(n squared), which means that, let's say today you have 1,000 qubits, 100 qubits, then n squared is going to be 10,000 gates. Is it a lot of gates? It depends on your decoherence. But let's say you have a decoherence of order 0.1%. How many gates can you do? And actually I'll explain why you can do that many gates. Number of gates is essentially 1 over epsilon. And so here, so this is 10 to the minus 4. So this is 10 to the 4. But I mean, once you get to this point, you're not so good. So here, it tells you that with the decoherence levels we have today, we could barely make it with a Fourier transform, but I wouldn't advise you to do it, because by the time you reach to 10,000 gates today, maybe on IBM you can get still get something, but without error correction at least. All right, and I think I'm going to stop here, and if you have any questions, I'm happy to answer them, or I'll try to answer them.